All right, welcome everybody to the panel on AutoML in the age of large pre-trained models. And we have 4 panelists with us today. We have Wang, Debadeepta Dey. Then online, we have Houlsby and Müller. I kind of prepared a couple of general topics that I think might be interesting to discuss, but this list is by no means comprehensive. And if there's anything people would like to discuss, please raise your hand. I have the mic here. Well, I think there's a lot to discuss, and I think it'll be a nice, maybe not that nice, exciting conversation. I explicitly thought it would be good to have diversity in the panel. So Z has done really nice work on using pre-trained models for hyperparameter optimization. Sam has done likewise work on using pre-trained models directly for AutoML. And then Debadeepta has done work on using AutoML to improve big models, so NAS for transformers. And well, Neil is the last author on the vision transformer paper, has previously also done some work in AutoML, so he represents both parts, but well, he moved from AutoML more towards the non-AutoML. So let's see, we might have some critical views. I had originally also asked Alexei, who's the first author on the VIT paper, and was previously a postdoc in Freiburg, and I know has always had a bit of a critical view on neural architecture search, because he just doesn't do any of that. He just does it manually, and he came up with vision transformers. So that is something that we as a field really need to take seriously, and we need to ask ourselves, what is the role of AutoML? What can we help with pre-trained models? How can we use pre-trained models in order to do AutoML better? So, I sort of clustered it into 4 topics. One is, well, each with, so 2 topics with 2 subtopics. One is AutoML for the very large models that we see these days. So tuning these models with hyperparameter optimization and with neural architecture search, that's sort of A and B. And originally I had also invited Greg Young, who has a Tensor Program 5 paper and the series of Tensor Program papers. And that is actually a really nice way of tuning transformers. Unfortunately, he got COVID and is out sick. But yeah, Debadeepta can also cover some of those angles because he knows Greg well. And so then the second big cluster of topics is using pre-training for AutoML. So using pre-training for HPO and directly for AutoML. We could also talk a bit about how to use pre-trained models within AutoML. So how do you actually select the right pre-trained models and its hyperparameters? Or how do we do NAS when they're pre-trained models? Can we exploit them in some ways for that? So lots of possible questions. And maybe I would give the word now to our panelists to, well, maybe introduce themselves, say a few words about their direction, and then we'll go into each of these different fields in a bit more detail afterwards. All right, maybe ladies first.
Can you all hear me? Oh, that's loud. All right, hi everyone. My name is Wang, and I'm a research scientist at Google Brain. So my work touches a lot on Bayesian optimization, active learning, and uncertainty estimation in general. And so speaking of large pre-trained model, what we've done is actually both way around. So we use So we try to pre-train smaller models in order to tune larger models better. So all of the work is on using pre-trained Gaussian processes on multitasks in order to tune the optimizer hyperparameters of large models on large data sets. And the other side is actually on active learning, where we use pre-trained model to boost the performance of active learning. And probably not surprisingly, without pre-training, active learning can't really do much. but with pre-training, we actually get a very large initial boost. Yeah, so kind of similar stories.
Thank you. My name is Debadeepta Dey. I just go by my last name, Dey. I'm a researcher in Microsoft Research in Redmond. And my background is actually back in the day of robotics and machine learning, but over a series of perhaps fortunate accidents, I just do fully neural architecture search now. And me and my team are also building Archive, completely open sourced, MIT licensed, PyTorch-based framework for neural architecture search, very much in the same vein as NASLib from Frank's group. What like relevant work to this particular panel and this topic for discussion today is our transformer search. And one of the things that we are very keen to do is not only figure out what are like good transformer Pareto frontiers for edge deployment and what should be good search spaces for such language models or even multimodal models, but how do we also scale up, right? Like, I think this is a challenge which is very difficult inherently for NAS and HPO jointly is how do we scale up models? How do we create the next GPT-4, but via NAS, right? Like, and this is a criticism I often receive from friends at MSR, like, like it's all fun and games, of course. And is like, Dey, how come this model didn't come from NAS? How come this is still coming from smart human beings, right? Both in vision and in NLP, like the big, large models. So I want to go back to them and say soon that, hey, we cracked it. Now you should just do NAS for large language models or any models, right? So yeah, thinking hard about that.
All right, who would like to go first online?
Sure, I can jump in. So my name's Neil and I work in Google Brain in Zurich. And I have dabbled, let's say, with AutoML and neural architecture search, perhaps 4 to 5 years ago with mixed success. We did have some nice success doing transfer learning with NAS-like methods. But then since then, I've been focusing mostly on computer vision and computer vision architectures and transfer learning. And like in many domains, we found that scale seems to be one of the #1 drivers of performance in transfer learning. So we've been working a lot on scalable architecture for vision and what designs scale best. And I must confess, much of that work has been driven by human intuition and also human tuning.
Yeah, and at this point, this should not be something you need to confess. It's something we kind of need to confess as a community, and we should be able, or we should hopefully be able to change this in the coming years. And well, let's see, AutoML 2030 or something like that. Everybody does this automatically. That'd be nice. All right, over to Sam.
Hi, I'm Sam. I'm a PhD student at the AutoML lab in Freiburg. And I guess I kind of have like a little bit of a mixed angle between what was said before. And that is, yeah, I can see how AutoML can change quite a bit by using very large models like language models to predict results directly and kind of meta-learn the tasks directly in the neural network. And we kind of can see that this works for small data sets already. And maybe this is a path forward for large data sets as well.
All right. Yeah, so one reason I asked Sam to be on the panel, he's in my group, he's sort of the heretic who said, yeah, I'm a deep learner. I'm going to come up with neural networks to do it all with neural networks. And he actually did. So he has this work that we'll talk about a little bit later on using these pre-trained models directly to do AutoML. But maybe we'll start with, yeah, HPO and NAS in the age of these pre-trained models. So we already heard from Neil, unsurprisingly, that this is largely done manually these days. So maybe the question to the panel, potentially to Dey, but also others, what can we do in order to change that? So what's the path forward? Of course, we can't run just RL or Bayesian optimization in a black box fashion, do 10,000 function evaluations. That's not going to cut it. What is the path forward?
Yeah, this is a great question. So I think I want to just introduce this, so because this has just been top of mind. And one aspect, if you look at the data sets itself, right? Like let's just put the architecture on the shelf for a second and the HPO for a second. The data and this morning Jeff Kloon's talk was I think the perfect segue. I was very happy that talk happened because I think it's on everybody's minds now. And this is something we are also actively exploring is. Can we come up with a subset of the data set, right? Like I give you, let's say, the concatenation of the pile plus 3 other big data sets. Now you have a 5 terabyte data set. If you are in industry, talk to your product group friends, they can give you data sets which are even bigger, right? Like if they are, depending upon the application, it's nothing. Now you have like billions of tokens, 100 billion tokens, not a problem. You have a data set. Now the issue, can we distill small data sets, much smaller data sets, and make it available to the community such that if you run NAS or HPO on this, now see what this immediately does is you can, if you can come up with a very high quality, small representative core set, and then you can look at core set literature, and core set has a certain technical meaning. It's a specific kind of data set distillation. But if you can come up with high quality of that, or like as Jeff Kloon was talking about this morning, synthetic data sets, which are small, right? Like 1% of the pile is all you need to do NAS with, right? Or HPO with, such that like in Greg's line of work with MuP, we can come out with now if you run NAS on this, or HPO with this, the minimas, local minimas that this induces has the same, will happen at the same locations on that than you would have on the big scale, right? So, which means that either argmaxes or argmins, whatever you get are respected, and you get to then scale up. On an 8, so just so that if you don't have access to a lot of GPUs, what this looks like immediately is if you get to have like 10% or 5% of the pile and you are confident about it, you get to run NAS on an 8 GPU A100 or V100 box up to pretty reasonably well. You get to do a lot of tries of different architectures very quickly, for up to 1 billion parameters or 350 million parameters, 500 million parameters. Yes, this is not 176 billion parameters off the bat, or like Palm 540 billion parameters, but you are no longer doing NAS on 0 to 20 million parameter range, which is usually what is common right now across all the benchmarks, right? Like 20 million is probably the largest model in any benchmark right now, tabular or surrogate or otherwise, right? So you get to go up by 1 parameter just by looking at the data set, if we can crack that, right? And we are trying to do that. I'll let you know how that goes. So that's one feasible line of attack, to just quote Richard Hamming. And the other feasible line of attack is, can we do Greg's? And because Greg is not here, I'm going to channel my inner Greg, is to come up with parameterization of architectures such that we can also think, we can predict by doing NAS at smaller scale, just as Greg is doing HPO at smaller scale, such that you can predict what the larger architecture scaled up would be if you can come up with that parameterization, but now across architectures. I'm sure Greg is thinking about it, and we would have loved to have him here, but that is another feasible line of attack emanating from the MuP line of work. But I will pass the mic on to other people as well. Chime in.
I can continue a bit. So I guess part of the topic that Dey was alluding to is what the actual goal is for AutoML, right? So eventually our goal is to improve training efficiency and minimize the time from where we probably have some data sets and then eventually reach a trained model. So we want to minimize that time. At least that's how I tend to understand that. And during that process, there are many variations. So for example, like we might have several different tasks, and perhaps from the beginning, we have some meta-learned knowledge. It takes a long time to train, but that's okay because eventually when we use that knowledge to train the models for all the other tasks, the total time will be much smaller than if we do it by hand. So in order to achieve that goal, I mean, of course, I think within this community, we all have some partial answers. But what I see as challenge here is for very large models, we probably can't even afford like 1 or 2 hyperparameter tuning runs. So in that process, like, are the Bayesian optimization approaches actually viable? I mean, that's the question that I'm asking myself. Because a lot of the Bayesian approaches we have now are assuming that, well, we might have, let's say, even the smallest scale, maybe at least 5 or 10 iteration in Bayesian optimization. But that probably isn't really the assumption in a very large model training on like gigantic data sets. So in that case, maybe our problem becomes, how do we run one round of training without really restart the hyperparameter tuning from scratch? But then once you go down that route, the problem becomes, well, if we just have one hyperparameter, if we get stuck, like how do we get ourselves out of it, right? Maybe the current way is that, well, we'll restart everything. But you see, like you get into this rabbit hole, and everywhere you have like some problem you need to resolve, and then you just don't really make progress. Yeah, and then there's the question of, I guess, when you're tuning the learning rate. So from the conference, there's this best paper award that goes to early termination. So that's the termination of the Bayesian optimization algorithms. But when we are training these large models, I mean, there still remains the question of like, when do we terminate it? Like, what's the right point that we terminate it, and so that like we don't like further tune it or do more architecture search or hyperparameter search. So I see these as the challenges that we face in AutoML, or to eventually achieve the goal of minimizing the total cost on getting the best model that we can get. But that definitely requires more effort.
Yes, I'm going.
Yeah, as a reply, I wonder whether I agree with you, Z, in that a good goal for the AutoML community would be to target these very large language models, like, I don't know, a possible GPT-4 as like the thing to tune, because for GPT-4 there will always be an engineer that you can pay to watch the training. So the GPT-4 training probably is like much more expensive than a salary. So for sure you can afford like humans in the loop. Do you think AutoML possibly is better than the ML engineer, or?
Good, we're getting into the
that
meat.
Question. Well, I mean, the way I think about it, I guess it's kind of not really like super aligned with the auto term, but I think all the software development is kind of like a collaboration between the machine learning method or AI method and the software engineer, right? Presumably people in this room kind of all do a little bit of software development, at least like coding. So I think the part of me as a software engineer, I build in a lot of things into my algorithms, right? And those are things that we tend to forget about when we're trying to write a paper about AutoML, about how like it's so great to automate everything, but we're forgetting the part that we're actually building a lot of knowledge. I mean, people might disagree, but I mean, from my point of view, I think it would be really nice if we can quantify the kind of knowledge or priors we build into the methods, and then like get a better sense of what are the things that we as software engineers are good at, and what are the things that machines are better at. I think in the past, I mean, it's kind of clear to, like before the machine learning world like dominated everything. But now, like because machine learning as a community tends to like automating things, right? So we become, so we started to like be in a state where we forget that we actually need to and probably should build in the knowledge so that the models don't need that much data to learn. Yeah.
I'll add a little bit to Zi's answer and to answer Samuel, is that I think we are very focused. We have the word AutoML, right? Like the word is auto. Perhaps we are missing semi-auto, right? Like if in the scenario that Samuel was describing, where if I have a GPT, I'm training GPT-4, I can afford to just pay a very skilled person to be on call all the time, watching the training logs, right? But even that, yes, we can, because the cost of that is marginal compared to the cost of GPT-4 training, but even that gets tedious, right? Like, so what I'm trying to imagine, what would this person be doing, right? Like they are going to watch the learning training loop go down, right? Like, maybe we can even put in automation that, hey, the moment it diverges or the dy by dx tends to fluctuate, or the second order of over some window, send me a massive email or a text, right? And then you jump in and you get to try to figure out what's going on. Maybe this is should happen, a more sophisticated version of this should happen inside a Bayesian optimizer, which is doing like, shadow trainings with small surrogate model of GPT-4, trying to find out like, what this tends to happen, for example, like, if you're doing server optimization, where any data that comes in, if you can afford it, you do a shadow execution through another pathway. People do this in databases all the time, where you try to see if like how quickly I would have given you the result if I had run this other thing. You don't actually put that in the critical path. You just do the normal thing. But if this thing actually retrieves the result very quickly, then you return that, or you learn from it and say, next time it comes, I'm going to bias it this way, so I'm going to use this pathway. So you could imagine that as that training is going on, you try to like, take the checkpoints, and as the training, you're obviously going to be saving very robustly the checkpoints. Take those checkpoints, start spinning off like, some small AutoML jobs, right? HPO jobs at very small scale on some small fractions of the data, right? So that when that your dedicated engineer gets that phone call or the text in the middle of the night that model training is diverging, let the system give you some options that, hey, from all the trials we have been doing on like where we saved, let's say 2% of the budget of compute to do this smaller surrogate trials, these are promising areas, avenues, learning rates you could go to, and give some recommendations. Like and if the person is just as skilled as Samuel, they will be like, I reject all of these. I'm going to try something else, right? So this is the back and forth, right? But this is extra data that then goes to your meta learner watcher, right? Like your monitor that is running in the background, thinking through, dreaming of other pathways the thing could have taken. And of course, you are going to do very tiny probes here. You can't afford too much. But this could be very useful to any corporation, organization, big science who is training like, the open source GPT-3. I think a larger model than that as well, to do better models, right? Without it being completely manual.
Yeah, Neil, go ahead.
So I think one of the challenges with training large models, so the obvious one is it's expensive and one doesn't have too many goes. But the second is that one's usually the first or one of the first to do it when one's training one of the very large models. So one doesn't have a large amount of experience to draw from. And one observation is that sometimes things that don't matter too much at a sort of medium scale or scale at which one can iterate, or a scale at which lots of papers are published, become very important at large scale. So it's those unforeseen factors that one has to get just right. You know, some constant in the system that you never bothered to look at suddenly needs adjusting when one's training, you know, 10 billion parameters as opposed to 10 million parameters. And so the challenge when, you know, setting up an automation system to, you know, probe for or look for and tune the parts is typically guided by the systems that have been trained or intuition based on smaller scale. And the flip side of that as well is that often things that are very important when looking at a smaller data set work in vision. So, you know, consider sort of average size data set, something like ImageNet, don't always turn out to be useful when scaled up. There have been so many times that I think I've discovered something interesting, only to try it at 10x scale to realize, nope, it's the same as the standard transformer or whatever it is. So I feel like pointing the search space in the right direction for large scale runs is really quite challenging until one's tried it and one sees what goes wrong that didn't go wrong before. And that's a little bit the nature of when one runs something for the first time or like, you know, or just a couple of times.
All right, great. I think I'd like to do an intermediate summary of this first part. So we've heard about, well, having really the prior that humans have is really important. As Neil says, it's not really the prior from data because nobody has done this before. So meta learning is maybe in many cases hard. Of course, if there is related data sets and we're in the AutoML setting, if you're serving a customer with like a big system like AutoGluon or AutoScaLearn or anything like that, or PyTorch, then you're in control. Then you can meta learn across data sets and you can do a lot of the pre-training, etc. But the other thing, if you are at a new data set and with a new type of model that you haven't trained before, well, you can still use these multi-fidelity approaches that Dave was talking about with Tensor Program 5. So you can scale down the number of epochs. You can scale down the data set size. You could, for images, you could also downsample images. You could actually look at less layers of the network, less wide networks, etc. So there's a lot of different dimensions, and I think it's really a challenge how to do that right, and potentially also how to combine that with human priors, etc. There's some work in Bayesian optimization to actually exploit human priors. We've worked on it. We had a paper at iClear where you just have a prior that, like, for Adam, probably the learning rate is something like 10 to the minus 3. You don't have the prior that Bayesian optimization usually has that, I think my function value will be 0.98 if your hyperparameter is set to this. That's not the type of priors you have. But the priors come from previous experience of the humans, but the data from before isn't directly applicable. You could also think about learning across previous code versions, etc. So maybe a final statement of people for this first part. What of these things do you think is the most interesting and most useful path forward for tuning big models? Or they're all important, just need to combine them, it's going to work?
All right, I'll try to start first and others can throw out more interesting ideas. So I guess like just for brainstorming purpose, I wonder if it's a fruitful path if we think about AutoML more as an interface rather than like a software package. So as an interface, you would still like I mean, so it's more or less like you're trying to assist a software engineer to get the best model. And perhaps during this process, there are different things that you can suggest like this person to do. And then there are situations where, well, you can monitor what they're doing, right? And perhaps this is not going down a very interesting path. Then it's almost like you have a system by your side, which are fully informed by data, fully informed by the kind of trials that we've seen before with different data set and different models, so that we can prune out some space of the search for the hyperparameters or model. And then at the same time, maybe the model is able to come up with really creative suggestions that we miss. So that's a setup for AutoML as an interface, which focuses more on how do we help people instead of how to get rid of them.
Yeah, we are definitely on board with using, like, as a way to, like, human in the loop AI system, human in the loop ML. I think the other aspect I would like to just to, like, if you're placing bets, and since I'm sure this is being recorded, we can come back to it in the next AutoML or the next one, and I can see whether I was right or wrong. I have my eyes set firmly on the data set aspect, right? I'm actively trying to see if we can come up with a smaller subset over which, like, especially for, let's say, can we reproduce GPT-3 training much more efficiently, such that then now we can do AutoML, NAS at least, or FNHPO at the, 50 to 1 billion parameter regime, right? So that's my crawl scenario. If I can do that, then maybe the learnings from that will allow us to go from 1 to 10 billion, the next order of magnitude. I'm sure Moore's law will also help along the way, but but just as a uniform interface, because I think there's just a lot of redundancy and a lot of just crawling the entire internet and dumping it into your database as a data set, I think in addition to all the fairness, ethics, transparency problems and legal problems, also is, I think, creating just too much CO2 footprint for training this. So I'm placing my bet on the data sets.
Right. Neil, Samuel, anything?
I think that's okay. I'll start. I think that's one of the keys is the data set size and finding the right proxies. It's curious that typically at the sort of medium scale, one does many epochs of one's data set, whereas someone's training the largest models, particularly in language, but also in vision, one's typically in this sort of one epoch regime. So when you don't see a data point twice, it's kind of different setup to 90 or 10,000 epochs. And I think finding the right recipe of data subset combined with ways of taking smaller models, maybe it's not just as simple as going shallower, but training individual blocks or something that gives like a nice predictor of like the equivalent blocks trained at 100x scale. I think would be perhaps the most sort of practical step that would be useful in the short term.
I would also kind of agree with Dave as well. I don't know. Greg Young's work was really inspiring, I think, in like tuning the learning rate on like a cheaper setup. And if you can this work was really like focused on the learning rate. So maybe there could come another work focused on another hyperparameter that's also important. I could see that like really working out even for large models.
Cool. So I think we can conclude for AutoML for large pre-trained models or large models in general. However we do it, the holy grail is that we do it fast. And looks like probably most people agree that the key problem is how do we find the right proxies in order to really scale up, right? For this first part, any comments, questions from the audience? Yes, there are some.
Thanks for the insight, Dave, for focusing on the data and the course part. I like this idea, but I was wondering, do we really need large model if we find the course set? Because it doesn't seem so. What is your thought about it?
But that's a completely fair point. We may not need a large model but one of the things is there is something magical, right? Like if you look at Sebastian Bubeck's best paper from NeurIPS, right? Like, where they showed that in order to, it's a theoretical statement, it's not practical yet, as that one of the findings is in order to guarantee robustness, adversarial robustness, size, there is no way around size. And if you buy Seb's theoretical argument via isoperimetry, then it becomes, yes, you kind of are stuck with a large model, right? Okay, I want to be very careful and not mislead people on Seb's work. It doesn't mean that small models cannot capture that. It's just that you may not be able to guarantee that you will have the same robustness unless you have this exponentially larger models. And this is where, and then if you look at it, there's also assumptions on like general placement of your data set, like there's no degenerate positioning of the data points. And I think this is where it may be, and I would be glad to be proved wrong, that we as a community may find ourselves not getting around large models, just from even like for differential privacy, federated learning, and all these adversarial robustness, these aspects. So if you want models that you want guarantees against, then you might have to just deal with a bigger model. And then in that case, the data set becomes much more important, right? Because that's the only thing you have direct control over. And of course, your architecture, like Node-Sebs lives out what the constants are in how large it needs to be. And we can via NAS go attack those constants, make those constants in our exponents much smaller, and such that we are much more efficient. And then that's where we can step in with NAS and HPO. But the exponents might still be there. I'm very happy to be proven wrong, but that's where my intuition leads.
Hi, so we heard a lot of different perspectives on, what AutoML is in terms of what you see, where it's going in terms of it being an interface or an enabler or something like that. And in the age of large language models, I was just wondering, in a bit more contemplative vein, what would you think would be, let's say 5 years from now, a win for AutoML in your perspective? So could we define this sort of thing that would suffice for you to say, okay, now AutoML has sort of created an impact, given so many techniques are under the umbrella and humans are also in the loop and stuff like that?
I think it's really difficult to predict the future. But I guess from my viewpoint, I think probably the more, I think the easier route is you try to combine the human knowledge in a very informative way, so that you don't need to collect all that much data in order to learn a very good model. And that including collect the data when we're tuning the architecture, tuning the hyperparameters. Those data points are very expensive. Since we're trying to automate some parts of it, of how people create the machine learning models, perhaps it's easier if we look at directly at how people tune it, right? And then see which part is easier to automate and which part is not. I think that might be the easy way, although I think there might also be other routes that could also lead to very interesting results.
I have one humble achievement, which that I want to aim for. Perhaps I'm just putting this on imposing this goal. I would like for at least for HPO and let's say for neural architecture search, right? Because that's what I'm primarily working on right now. Is 5 years from now at the AutoML, it shouldn't be that JAX or PyTorch is the go-to tool. I would like Archi, NASLib, or similar tools to be the first tool that people use instead of writing PyTorch or JAX code directly for their model.py. Same for like, instead of hard coding what the optimizer is and what the learning rate schedule is, because somebody said this is the right thing, and all the previous papers said like, where we just automate these away and set it, and that becomes the dominant paradigm from the get-go. I think that would be a huge win for the AutoML community. Like Alex was saying in his keynote yesterday, that in 2010, linear regression was the homework problem, right? Like nowadays, implementing ResNet is a first homework problem, and that's super easy to do. Anybody can do it, right? At the first year grad student or master student, or even high school student. So can we get where NAS framework or a NAS plus HPO framework is just out of the box, like every data scientist, research engineer everywhere just uses that instead of even trying to download efficient NetV0 as their first model. So I think that would be a good win. Okay, and yes, that is perhaps an achievable win, and I would be disappointed if we don't achieve that in 5 years from now. And the next thing, like the more ambitious one would be where the next GPT-4 or whatever big large model comes from NAS. I think we need that. Mostly, I think just personal ego. I want it out there. I want to say it to my friends who are always like, "How's come Palm is not from NAS, right?" And I want to channel that energy back and prove them wrong.
Yeah, I fully agree on that. So discovering neural architectures from scratch, from AutoML, that's really it. In 5 years, I do hope that the next transformers and so on will come from NAS, and that we already had a panel at the NAS workshop where, there was definitely the holy grail topic coming up with qualitatively new architectures. Sam, Neil, any comments on the last question, or?
I guess you just touched upon it. To follow from the previous point, it would obviously be a big win if the frameworks themselves, like PyTorch, were replaced by a neural architecture search-like equivalent that sort of made the human intervention even more high level. But I think indeed it would be another win if a piece of the library was derived from architecture search. I think it would be really cool to see a block like a normalization layer or an optimizer or some piece of the system that was invented purely by AutoML, published under its own right and receive 10,000 citations, right? Not the technique that built it, but the thing that was discovered, gets published under its own right and, accrues the adoption that all these handcrafted bits and pieces that are used everywhere. So I think that would also be a very nice win.
Maybe a short question for Neil, as like an expert in how to train these large language models. Like obviously humans use a lot of reasoning when they do this. And I was just wondering whether this is an opportunity to actually think about this. Can we use reasoning into AutoML systems? Because right now we don't care about this so much, right? And we just let BO make mistakes and then go the other way. But maybe for these large models, that's an opportunity to think about how to do reasoning. Do you think that will work or could work?
Yeah, I guess sort of the term reasoning is perhaps slightly abstract, but certainly I feel when a sort of a manual designer goes into a sort of unknown environment, they collect a lot of additional information beyond the validation loss to sort of narrow down where to look. It's the logs from the system, the speed the thing's running at, like the entire learning curves, gradient norms, everything, and sort of can sift through that to look for outliers. And that can give a clue as to why something isn't working as intended or something's working well. And so Yeah, I feel that without all that information being readily available to an automated system, it's going to be quite difficult to sort of explore beyond the areas that have already been explored, unless you can just try thousands and thousands of times and look at validation log thousands of times.
Great. I would then go to the second part. So from how can we use AutoML in order to make large models better, to how can we use pre-trained models in order to make AutoML better, or in order to do AutoML. And yeah, so there I'm gonna address Z and Sam to each maybe say a little bit about their work in this field. Maybe this time Sam first.
Okay, yeah. So yeah, our work in using big neural networks for AutoML is really currently we try to replace the standard frameworks like AutoGluon or AutoSKLearn, at least for some tasks, with a single neural network. So that would mean a neural network that accepts a data set and then spits out the labels for the validation set in one go. And we do that, only for smaller data sets, so like up to 1,000 examples so far. So, but we see that this is actually not as hard to do as we thought it was. It's kind of, yeah, it's not so hard. And we work on this in like the realm of training on artificial data, on artificial data sets, and then only only doing evaluations on real data sets. But one could do this, of course, also by training on real data sets beforehand, and then evaluating on real data sets or so. But in general, the method is all about one single neural network. You feed it a whole data set, including the validation examples, just without the labels, and it spits out the labels. Yes.
Yeah, Z.
Yeah, so I think in spirit comes out similar to Sam's work. So we have, I think I can mention like two works along this line for hyperparameter tuning. So, they're kind of similar in philosophy, but also very different in how the methods carry out. So one is about how to pre-train smaller models in order to tune the hyperparameters of much larger models. And so there we developed this technique called pre-trained Gaussian process. And so we basically, instead of hand setting the Gaussian process prior, which oftentimes, although I work on Bayes optimization, I don't really have a good sense of, like, especially in high dimension, what those priors mean exactly and whether they fit the function very well. I can get it from some statistics, but not very intuitively. So we try to replace that part of like setting the priors by hand with training the Gaussian processes on multitask data. And then we use that particular Gaussian process to do Bayes optimization. So the other line of work that we did is, so it's called OptFormer. And one of the audience, Richard Song, is actually also among the, is also here. And there we actually trained a transformer to predict what is the next hyperparameter to evaluate. And we pre-trained that large transformer, probably like a few hundred millions of parameters on some real world large Bayes optimization data set we have. And I think it's also pretty surprising to me. It actually was able to do very well. It's able to match the performance of the Bayes optimization algorithms that it tries to train with, and sometimes actually surpasses the Bayesian optimization methods that it get the data from. So there you have like two routes, right? One is training super large models with a lot of data points, and one is to pre-train like small Gaussian process models with comparatively much less data. Yeah, so those are the things I can think of.
Yeah, and I see a lot of parallels between these two works, which is why I think it makes a lot of sense to discuss them together. Especially the OpFormer, it's automatically learning to do hyperparameter optimization, and it also has this component in there where it predicts the Y value that is that you're going to get with a new hyperparameter setting, very much like the prior fitted network from Sam just predicts a new Y value with a GPT-3 like model. And yeah, so you automatically learn a hyperparameter optimizer, and Sam automatically learns an AutoML system. And this AutoML system, just to tell you how radical this sounds, it's in a second, you put in a data set, in a second, it gives you the same performance that AutoSQL gives you in an hour. And it's a single transformer. And of course, this is small scale so far, but it could be really transformative to the community. And I think it'd be really useful to talk about this. How can we make use of these things? How can we make them better? Where are issues? I think this maybe we can have as an open discussion with everyone. The panelists would, of course, be invited to speak first on this. But also the audience could be a bit more integrated into the second part. So any thoughts on this?
Hi, great talk so far. So with transformers, we can incorporate a lot more kinds of data. So I guess my question is, how long until you think we can start using all these transformers to incorporate all sorts of data, like a lot of multimodal data, incorporate that into one machine learning tool that makes the task of a data scientist or whoever's trying to get predictions a lot easier?
So have you seen the Gato model from DeepMind, the one for robotics? So they transform all modalities. So they train a model for a robotic manipulator to do various kinds of tasks, and all inputs are transferred into a sequence of tokens: vision, text, that the human is speaking, audio, speech. Everything gets fed in as multi-channel sequence, just tokens. Everything just goes in, and it's a transformer model. It's about, I think it's relatively small on the orders of as how big large models go. It's, I think, less than 1 billion parameters, because they just wanted to be super real time, because so that then you can it can interact with the robot and do things without it being too delayed of an inference time. So I think that in some sense, to be glib, the answer was yesterday. Yes, it already is starting to happen. And if you look at also the large multimodal models, right? I think if I'm going to bet a very expensive dinner that every large industrial lab is working on very large multimodal fusion models, right? And you can already see some of those papers coming out, but just unimodal data is and most of the work, right? From there, and this is also very interesting, right? Most of, if you look at the breakup of those teams in those large industrial labs, 80% of the team is working on the data set. 10 to 20% of the team is working on training models, right? So because the data set curation for fusing multiple modalities, cleaning them, that's actually a huge amount of work, which also leads me to think we need in AutoML, we need to do auto data something. And that's a latent need because, and if you go to any human in the AI loop sessions at conferences, ML or otherwise, you will find that vast majority of the machine learning lifecycle is just data, creating data, cleaning data. Actually training the model is one of the lowest parts of the entire burden, right? And what you are suggesting, yes, it's starting to happen, which means then creating these fused multimodal data sets is going to be even more painful, right? Who's going to label all this? Who's going to collect all this? Yeah.
Okay. Any further comments? Otherwise, we go to the next question.
No? Yeah. Thanks for the discussion so far. So we have two panelists that have now transformers doing hyperparameter optimization. But Frank was talking about coming up with qualitatively new architectures, new pipelines. Could these models also lead to doing that?
Yeah, I could answer. I don't think so. Not soon. Not like before we see GPT-4 doing things that we think are really human, I would say.
So one comment on this topic, and it's a bit of a speculation, but we were speaking earlier about having a combination of sort of human-guided design and AutoML to sort of co-pilot with the human. But there is also another sort of view to it that sort of human model design is quite compartmentalized into the bits and pieces that, like how the sort of code is written. You have the architecture and then the optimizer bit and regularizer bit and such. And whereas for the AutoML solution, I'm wondering if one could sort of look one level lower at the program, with AutoGrad, fully written out, which is just, a program that has a bunch of variables and does some algebra and then adjusts those variables. And one could change that program automatically in different ways that maybe doesn't really conform with, okay, this is like a change to the self-attention or something, like some compartmentalized piece that is used as part of this sort of human design process. So I think in order to build something new that isn't, maybe it won't be called Transformer 2, it'll be a change to the program that sort of doesn't fit in the standard boxes. I said that was going to be speculation a bit, but I think that's an exciting direction. I've seen a little bit of work maybe in that direction, AutoML 0 and such. I'm sure there's more.
But like as a direct reply to this, do you think this could happen before there are major successes in designing a single layer with NAS or a single optimizer? Shouldn't one start with a simpler problem of following this human? Yeah.
Well, maybe and it's by designing a single layer, one's up against the human in the region where the human is at its greatest strength. People have been thinking about layers and can sort of reason about what self-attention is doing very easily. But humans maybe have a harder time sort of reasoning about, okay, what exactly is the extra optimizer hyperparameters doing in there and the effect on the system, and it's harder to do design in that space because one has less intuition.
So I just want to make sure I understand the question. Did you say like transformers, can they solve AI or?
Yeah, sort of could new types of architectures also help us in building better HPO algorithms and building better AutoML algorithms and so on.
Oh, I see. So like.
And then you can see, well, the optformer says, well, it's a transformer that optimizes a transformer. It also, yeah. it could go in that direction, but I don't think the question was going quite as far. But I think we have time for maybe one more question, because we do want to be on time to get on the boat, so it doesn't leave without us. So one more question, and afterwards, as a prep, I'll also ask everyone for a final statement, give you a chance to say anything that you wanted to still say. But first, one last question. All right, excellent. So then we're already going to this final statement. Who would like to go first?
I think I would also like to add, like, just to piggyback on the previous discussion, is that, you know, some of the components are starting to be actually useful, right? Like if you see the primary easy paper who are doing program synthesis style search, they come up with like 2 components that they injected into other code bases, and it immediately gave a big boost. And I can verify personally that the ReLU squared, so they found by just doing this, that ReLU squared, this is not, I don't know what you would need to be eating and drinking to come up with ReLU squared in your transformer block. I would not, right? So maybe Samuel would, like, you know, I can see him coming up with ReLU squared. But if you have your transformer model, especially for like text generation, so they did it mostly for text generation and text to text sequence tasks. Instead of ReLU, square it plus -3 perplexity immediately, right? Like, you know, so and that was, yeah, I was like, this is useful, right? Like, and I can just, I mean, like, this is not a weird architecture, put your main architecture, but just ReLU square it. But they found it via neural architecture search, right? But at this very low level, yes, it's they had to do tricks to make it actually work, because most of the programs didn't compile. But it's promising to me, because that means that, hey, there's unintuitive things that NAS is finding, which is already useful, right? Like in all our transformer code base, we're like, just use ReLU squared. Like we have this option, like minus, primary easy on or 0 or off, right? So dash, yeah. So perhaps it might happen sooner than you think. And on that positive note, I will end.
All right. I'd like to go next.
Okay, I can continue. So, I mean, I think eventually it's about like how do we formulate the problem, and with whatever method, whatever we put in, how do we solve that? And as we were talking about earlier, so if the problem is really about saving the computational cost and minimize, and also like saving the human effort to eventually come up with the model that that works with minimal amount of time, then in order to do that, yeah, we can definitely throw in all the methods we have so far, and as well as consider things that we haven't considered so far, like as Neil was talking about earlier. We tend to forget that fact that the way we construct softwares tend to be compositional. And in that case, would AutoML have a relatively, like, I guess, easier life if it's also trying to design more compositional models instead of just like one black box, right? And then like, I mean, I think like one topic that we probably didn't really touch upon is how do we understand the model we put together, and that probably also touches on a deeper question on like how do we understand deep learning, and is it the actual way to go? I guess like in AutoML we kind of assumed that. But in reality, if we want to deploy the model in like safety critical applications like healthcare or robotics, like autonomous driving, then we need to have some sort of certifications on like in what circumstances our model work, in what circumstances let's not trust the model. And that's something our current model isn't very good at. Then can we use AutoML to do that? I think that would be really powerful.
Sam, maybe?
Yeah, I don't have much more to say. Just I think, yeah, we have very powerful neural networks, and we shouldn't forget that we can like do all kind of things with these that we don't expect that work. That's super nice, and I think even we as the AutoML community should also make use of that and don't just ignore that and say like, oh, that's the others. We have different methods.
Yeah, if you can't beat them, join them.
Exactly.
Yeah, lots of really great points. I totally agreed with the one earlier from Z, that it'd be cool to see AutoML like compose pieces together rather than try and build the whole thing from scratch. I think that's a great idea. I think on the topic of building GPT-4, which came out several times, I feel that to Transformer plus Adam has been around for quite some time, and I feel to make a step change, probably one has to change two things at once. I think it's going to be challenging to stick with the whole system the same and just tweak one part, the architecture, or just change the optimizer. I think probably one needs to change two things simultaneously to reach a new optimum, whether it's the data pipeline in the architecture or the ratio of scales, and the optimizer and the architecture, right? And I feel like maybe AutoML, like at the right level, is a way to do this sort of search and screening of the huge number of combinations here, if one can sort of design the search space to be general enough.
Awesome. Those were really nice final words. And with that, I'd also like to close the panel. I think people need to slowly leave for their Ubers and buses and so on. So yeah, I'd like to thank the panelists a lot, especially Neil, who jumped in today. So thank you.
Thanks, bye.
Let's see where we get in the next 5 years, and then we can see which of these visions materialize. Thank you.